LOA, let's see here. Okay, so LOA was developed by ERL, Environmental Research Labs in NOAA back in the 1970s. It simultaneously measures the average crosswind across the optical beam, and it measures the turbulence over that measurement path. So we can actually shoot up to 10 miles with this sensor, and it'll measure the crosswind and turbulence. So path average sensors are going to be a lot more accurate than like a single point anemometer. A lot of people will use just a single anemometer. Sometimes you use an anemometer that maybe is at an airport 20 miles away, but that's probably not what the wind is at your location. So LOA offers a more spatially averaged representative measurement than a single point sensor. It's really a versatile instrument with a lot of potential. It's not something that EPA is going to tell you to use, but it's something that is available that you can use along with your sensor or even a passive sampler. When you think about the advantages of LOA technology, we're doing a path average, which is more representative. So we're going to measure that path along that whole line. It's an eye safe technology, so it's not going to burn your eye up if you happen to look into the beam. It's portable, so you can set it up if you want, or you can set it up on tripods. We've done that for NASA and a few others. The military uses it that way. It can hook up to a laptop, so if you're trying to do something and want to hook up, you can do that. It has a long range, so we measure from 200 yards to 6 miles. Actually, it can do about 9 miles. It has Modbus RTU or simple ASCII delimited string, so it'll send you a signal. It's powered by AC or DC, so if you want to power it by a car battery, you can do something like that for the field. They can be placed in safe areas. So the thing that you're wanting to monitor, so you can kind of place it far away. And I'll go over a couple of applications where they're using it like that. When you're looking at the installation of an LOA, again, it can measure up to 10 kilometers. A single LOA is going to do bidirectional wind, so it's going to measure crosswind, right? So if you have a plant next to your plant, you're worried about emissions or your emissions being reported from that other plant, you could potentially set an LOA up between the two sensors, and then you're going to get that path average wind across that whole area. And when you think about that, you have a long space right here, and maybe you have a big air intake that'll change the wind in that area, or maybe you'll have a gust at one end of the plant. This will path average that whole area. So instead of looking at a single point, you're actually looking at that whole area of wind across that whole area. If you do two LOAs, let's say set up in like an X pattern, then you can get the X and Y axis, and then you can measure the magnitude of the wind direction and the wind vector. So you'll get what's going across that whole area, and it's almost like a giant anemometer. If you do 3 or more LOAs, you can do an equilateral triangle, or you can enclose an area, and then you can understand the movement of air over that large space. So you close a large area and then understand what is going in and out of that area, crosswind wise. What's going on there? You can use retroreflectors on towers or stacks to measure vertical profiles if you want to shoot up. So you don't want to put a receiver or a retroreflector on a tower that's swaying, but if you have like a building or a window, you can shoot out a window or shoot from one building to another, so you can shoot up high. There's a lot of different ways that you can use these. You can shoot from buildings or out windows. You can shoot over water. This is an LOA that we used to measure wake vortex off a jet aircraft. So NASA did a study at a couple of airports where we were measuring the wake vortex off a jet aircraft. It just proves that we can actually do that. This is kind of what I was talking about with the single path anemometer. If you think about it, we're measuring the path average wind and the relative to that direction that's blowing across that path. If the path is pointed, let's say north-south, and then a 10-mile-per-hour wind blowing from the west, let's say 90 degrees to the path, it will represent as 10 plus miles per hour, plus or minus 10 miles per hour, depending on which and the transceiver's on. And then this is for the meteorologist out there. So I kind of added these slides. The same thing, if it's blowing from the northwest, SIN 45, then the speed is to be about 7 miles per hour. So there's different things that you can do to get a better understanding of what the wind is doing. Long baseline optical anemometer. So basically an optical anemometer. What it is you have like a infrared light, LED light shoots across, and then you have two 6-inch detectors. And what we're doing, and I'll go into that in a second here, is the temperature in the air is not uniform. So you'll have pockets of air, and those pockets cause shadows on our detectors. So that's what we pick up. It's going to be better at the LOA is going to be better the longer the path, because you can have better resolution. Once you start to get to really small distances, it's almost better to just use like an ultrasonic wind sensor for an application. Let's say you're looking at 60 yards, you might as well just use 2 of those instead of ours. We could shrink the detectors down, but your numbers may go up, so maybe you don't like that. When you're looking at 2 LOAs, if you do 2 paths at 90 degrees apart, that would be the most accurate. But let's say you can't do it at 90 degrees apart, you can actually set it up a little bit off, and then 20 degrees off, and then in the software you can make some of those changes. If you want a graphical display that displays the data, we can develop that, or we can bring these 2 LOAs into what we call a DCU, and then send that data to your control system or your software that's doing that. Same thing with using 3 LOAs, or if you surround an area of concern. When you're looking at what you do is you use at each lag, it'll measure the crosswind along that optical path. Then by averaging the wind vectors on all sides, it'll give you the average 2-dimensional wind area over that large area. So you get one area, you measure that crosswind, you get another one, you add all that up, and then that'll help you get, by doing that, you can start to look at the convergence and divergence of all the wind vectors. So that's how you use LOA that way. And this is just kind of an example of there was a, this is Washington. So if there was a hazardous explosion or something, we could track that. When you think about the capabilities of LOA technology, people use it for micrometeorology, convergence, divergence studies. They used it for the wake vortex study. You can obtain the 2-dimensional wind profiles. You can measure updrafts and downdrafts. It can be difficult. Sometimes you need to add more sensors. The military uses it for plume dispersion and weapons testing. Again, you look at crosswinds. If you're looking at CN2 strength, most of you guys are not going to be worried about CN2 strength. That's mostly for airports, but I put it in anyway. Microbursts and vertical profiles. So that's some of the things you do. When you're looking at optical scintillation, we're basically looking at fluctuations of light and temporal cross correlation. So what happens is, as I was mentioning before, you have these different temperatures in the air. It's not uniform. So as you shoot a beam of light in that, it diffuses that light. And we have 2 detectors right next to each other, a known distance apart. And basically what we're doing is we're clocking the speed of those shadows as they pass the detector. So you see a shadow, like there it is in detector A, here it is in the detector B. How long did that take? And that'll be what your crosswind is. And it's bidirectional. So we use both ways. This is just kind of in a slide where I'm showing, I probably don't need this one, but has little pockets of air. We take 4,000 data points every 0.3 seconds. So we're taking a lot of data here. So we're taking tons of samples, so you can drop, something misses, but that's why we can be really accurate on this. So we take 4,000 data points. You see the little blurb in detector A, then you see it in detector B, and the opposite directions this way. This is basically how it is. You have your light, and then you have your 2 detectors, and then inside the control unit and digital processing, and then that sends the data out. Some of the successful applications that we've used this in, the aluminum industry came to us because they had to measure the roof vents off of their processes, and it was about 3 kilometers. And they were using a technology. They were using anemometers, and they were eating up, and they were buying them every 6 months. So what we do is we took LOA and we shrunk it down a little bit, and we shoot a path over the aluminum pot rooms. The EPA accepted it. The only reason the EPA accepted it is because industry came to EPA and said, we want to use this. So if you want to use our technology or any technology, what I would recommend is that you go to EPA and say, this is the technology that we want to use. Because if you tell them that you want to use it, then they'll go, okay, let's look at it. But if you don't, then they're going to. So the best way to get your technology approved or to use a new technology is to go to EPA and say, this is what I want to do, and we'll show you why it's good. So we got method 14 approval on this, and that was a really successful application. So we're in a lot of aluminum smelters. Another path average study that we did is drifting of wind from Greeley in Denver. We were kind of seeing it was so we were doing these path winds, and what we tried to do is we looked at 10 different anemometers, and then in school, so we had to set up these 10 anemometers, and then we got our beam across that same distance, and we pretty much got it pretty close. The anemometers, the wind, because you might have a gust or something in the way, so they can kind of difficult to do studies with just single anemometers. So this is another tool that you can use. This is another study that we did where what we did is we looked at a meteorological tower. It was at 300 meters and it was surrounded by an optical triangle. So we had 3 LOAs covering a 450 meter equal triangle. And there was a bunch of portable mesonet stations that were all around the area as well, detecting wind speed, direction, pressure, temperature. The wind speeds of the optical triangle, there is a linear relationship indicated by the line. The wind was on that tower, we had them at 10 meters and up to 75, like 100 meters. And really what we're looking at is below the inversion layer. So we were looking kind of lower, but the scattered diagram looked really good. When you look at the horizontal wind and the spatial variation, the difference between a monitor and open path is significant here, because you look at how the spatial variation of the wind is large, and trying to study bodies of air is really difficult with just a single mass station. So if you're trying to understand the idea is that if you add LOA to your program, that will give you extra data, right? The more data you have, the more accurate you can be. So, I mean, around your whole plant, we can do the whole plant, so you don't want to look at, like, somebody wanted to do one the other day, they brought to me and it was like 60 meters. And I was like, the resolution is just not going to be good. I would have to I could modify. If you're looking at just like a smaller area like that, maybe just use a couple of ultrasonic, be better. But if you're looking at a large plant and you want to surround that large plant, we could do that and then say, this is what's going on around that whole plant. So if a disaster hit, you understand, like, okay, here's this huge area and what's going on. This is where I was talking about the tower, the scatter diagram and tower measurements at 10 meters. The agreement is good, but it's not perfect, right? But when we did another study, what we did is we did one where we did modify one of our OFS units for a shorter path length, and they used us along with, so they used an LOA technology, and then they used a tunable diode laser, and then they had these passive sensors that they were measuring methane and ammonia, and it was at a waste site. So what we discovered is South Coast Air Quality Management District did the study, and at the beginning, the wind was blowing at a steady pace at maybe 4 feet per second, right? However, like halfway through the study, the wind kind of dies off, and then later in the study, it starts to pick up. So what's interesting about that is the flux through the measurement is not affected, even though the flux might be, right? So if you have air building up, so you have pollution building little area, if the wind isn't blowing, it's not going across. If you have a passive sampler, it's up those measurements. What happened was, I just think this is really interesting, is they had or comparing the source concentrations to the tunable diode lasers and us when there's no, the actual numbers of the radiometric method were higher. So they were actually measuring higher numbers when there was no wind because it wasn't dispersing, right? So now you have, if you look at the tunable diode compared to the, which is the direct method versus the radiometric method, like if you look at some of these numbers, the middle can be a lot different. Like you're looking at 0.28 pounds per hour versus point. So if you're not measuring wind accurately, you know, are you, and you have passive samplers, are you actually over reporting? I don't know. You know, it's something to think about. I think there should be more studies on that, but it does give you, you know, idea other kind of sensors that are measuring all the time. And if you're measuring across that area, does that affect how, what the wind does, right? When you're looking at, this is sung out at on the van up at a thing. So we were looking up at 12 meters above the ground and then 1.5 meters above the ground. And what we noticed is the turbulent CN2 data that at higher path lengths, the red line, the CN2 about a factor of 4 to 5 lower path line. But then through that test, we swapped the heads just to see if there was a difference, and it kind of said the same thing. If it's, you know, if you're measuring up higher and then down lower, you're going to have more turbulence, right? But what we did notice also is the agreement of the crosswind, which is really kind of what you're more concerned about, is the crosswind. What is the wind doing? Is it going towards a school? The crosswind kind of indicate that the crosswinds is not as sensitive to CO2 or CN2. So depending on how you set these up, if you want to set them up around your facility, you can kind of get a better idea of what the wind's doing and where that pollution that you're monitoring is going. You can always use a you know, a single met station, but the problem with the single met station is if you have a met station in one area, that's not going to be what's going on the other plant. It's very difficult to understand wind with just a single met station. If you're using a met station at another location, like 20 miles away, that's not going to be. So if you're trying to warn people about, hey, pollution's coming your way, and you're using a met station, you know, miles away, that's really not going to give you the data that you need. So either having a permanent met station or using LOA or having a portable met station that you can an emergency is probably a good thing to have for your teams. So when you think about LOA, it measures the true crosswind averaged across that optical path. So, you know, therefore the flux through that path measurement is not affected, even though the flux through other direction might change. If you use, it's an optical measurement, so it can measure spaced average two-dimensional wind velocities area. There's really no other sensor that can do that. We're the only ones. These spaced average two-dimensional wind measurements are more representative of a large area wind than a few anemometers or single point institutes can ever be. We set up two LOAs in an X pattern. It'll measure the magnitude of the wind direction and of the wind vectors. If you want to measure the average horizontal wind velocities, they can be obtained by measuring the side of the triangle. And then if you combine LOA with other sensors, you can better understand the mass movement of hazardous wind. So we're looking at LOA as like a tool that you can use with sensors. So if you're using either open path gas detectors or gas detectors spread out throughout a facility, we're going to help you understand what the wind is doing around your facility. It's not cheap, you know, you're going to spend some money if you want to do something like this, but it is available. And if you are interested in that kind of thing, you know, definitely let us know. I'm going to tell you have to do. They'll say just use met station somewhere. But these are some of our users: TR, Alcoa, Defense Department, NASA. They use, you know, EPA actually has an older version of this. So there could be more that could be done. But if you're trying to understand what wind's doing, or if you're worried about your neighbor, you know, up there on your thing, and you want to get a path average wind, you could definitely use LOA technology to better understand that. So that's basically the presentation. Does anybody have any questions or?
What's the size of the LOA?
I mean, we're talking about like this. It's kind of like a standard FTIR. It's about that size, and then the detectors are 6 inches. Each 6 inches, so it's not. Should I have? Now this is in my computer, so I can't show you my pictures. But if you look at, let me see if I show this one. No, that's actually a different one. I'm off to the side. This is the LOA that we used for that we modified for aluminum smelters. But if you're looking at LOA 105 or 005, this is the one. Let me see if I got it here. They're basically up on top there, so you can see those. So that's basically what we're measuring right there.
Once you set them up, you have the receiver as well, and they basically stay there. Or
you know, normally what you do is I mean, it's a research instrument, so
yeah,
you know, I don't know what these guys are doing, you know. Normally the idea is that you set it up and you have a receiver there. You could potentially put it on some sort of a thing that would say, okay, I'm measuring here, and now boom, I'm going to move and have it pivot and then measure that way and measure, here's this, and then go over here and measure that. You know, there's obviously going to be some development in that, but I know they do that. I think Spectrum does that on some of their FTIR, and I know some other people that have done that. So, and you had a question?
Yeah, two questions. First is, do you report the uniform average of the optical path, or is there some weighting function based on where?
We're measuring the path across that whole area. So if you have a large area like this, I was talking to wind. The problem, it's not really a problem, but you could have a gust of wind right here in that. We're going to average that across.
But is your response function, if I have a gust of wind next to the detector, is that the same?
It's going to average that with everything across that. Yeah.
Okay.
Yeah.
And then how long is it?
I mean, if you block detector completely, you'll probably have problems, but it can work in a lot. We'll be fine. We measure, I mean, we have sensors that actually measure rain that uses the same technology. We can measure rain and snow, and the National Weather Service uses it, and they actually calibrated the radars to our weather sensors. So, I mean, obviously, if it's coming down so hard that you can't see a thing, that could be an issue. Or if it's snowing and there's so much snow that it's like a blizzard, sometimes you can't get it. But here's the thing: we only need 0.5% of the light to get through. So we're looking at fluctuations in light, not absolute light. So if you have 5% getting through and wind's blowing and there's like, here's a, you know, the light's still shining no matter what, and it goes, there it is, there it is, there it is. You can have, because we're taking 4,000 samples every 0.3 seconds, you can have these intermittent things. You drive a truck on the thing, forget about it. You know, it's kind of like the same thing with any other operator, you know. So, anybody else?
The patenting for other pieces, you know, or the other end, you know, how.
Yeah, you don't want to go. Yeah, so if you go, I just talked. So if you have an application where it's like you had when you brought me the other day, it was 60 meters. Yes, if you have like 60 meters, resolution is not going to be there, okay? Because we're looking, the detector is looking at 6 inch, right? So looking at different temperatures of air, right? Because air is not uniform, so there's like little bubbles in there. So if you take a 6 inch detector and put it 60 meters away, I'm going to probably saturate it. But what I can do is we have this thing that you can drop over the receiver, a 2 inch detector, but the resolution is like that. It's really not. But we do have and then I'll tell you if we can do it or not. Got kicked off here. Yeah, so if you So on the shorter paths, you know, like I told Troy, I was like, it was 60 meters. You might as well use 2 anemometers. It makes more sense. Do it, but it's really more for large areas. So if you're looking at a larger area, you know, there could be studies done, but it's, you know, all that costs money.
As far as as long as you can keep alignment.
Yeah, and it's dispersion, so it can go like that. So we can go up to like 9 miles. Really far. Not everybody does that. You know, I mean, there's most of the people this technology are like NASA, the military stuff, Alcoa, you know. So it's like industry came to us and we're like, hey, can we use that? Yeah, and some of the, yeah, I'd love to be like to us, but I'm like, you know, 2 anemometers, it just makes, you know. So there's some applications where you're like, I want to measure shorter, but you want to measure in a smaller, like fast goes to 40 meters, right? So we detectors and you're looking at a 2-inch path length, resolution will be, but is that really the best way to do it? I don't know. Maybe not. So it's, you know, there's a lot of money involved here, but if you're trying to studies, if you're looking at a large area and trying to understand a large area, I would say surround an area well away and then use different detectors like either open path sensors or point sensors, and then place those around to get a better feel for what's going on. But yeah, so I mean, it's challenging because you're like, I wish I could be like, yeah, buy it, you know, but these things are so hard to sell, and it's really like a research instrument, you know, to think about it that way. So but it does validate an open path sensor, right? So if you're looking at an open path and you're using a single point anemometer, it kind of defeats the point of what you're trying to prove. So one is an open path sensor across that whole area. But, you know, I feel like you could use a biodigester, you know, might be big, but. Also have any other questions? No. All right. Well, thanks. We appreciate you guys coming. Any questions, just let us. We have a booth. It's not set up, but no, it's in UPS 11. So just let us know if you need anything. Thanks. Yeah, yeah. Thanks, man. Yeah.
Monitoring for this room. What's this?
Yeah. A new way to measure gas is required for IoT.
Okay.
Where are you at? Are you in?
Here at 10:15.
Yeah.
I tried to upload my presentation to the website. I
So hard.
get in, so
Yeah.
I just brought it on a flash drive.
Yeah, I put it out here.
Did you go to the 7 o'clock presentation?
I got right as he was ending. You know.
Is this the next one?
Oh,
This is the next one. New way to measure toxic gases with wireless.
Oh, change the schedule last week then.
I believe so.
Okay.
I looked at it. Yeah, they haven't changed a whole lot. See.
I know, I have
Mr.
one
Gibson.
that does anemometers. They had me doing that in the flare section. I was like, I should have done that here.
Because there's a gap right before I talk, so it's.
Well,
Sorry.
yeah, I mean, I could do a talk. I have a talk that I should go talk to them that they had me doing on.
Oh, sorry.
It's okay.
Yeah, that's so.
Oh, yeah, they moved one of them. Okay.
Yeah, because initially there was supposed to be a gap after this presentation.
Yeah,
Yeah, there's that gap right now, and then there's an outside, it looks like there's an outside spot on that schedule. And just see if I
who you with? Who? What do you guys do?
We just kind of go out. They got Gary's about the technologies are out there that are doing. Different types of things.
Are you guys like the one sensor? Like, I'm doing another talk on this thing called Hazmat. And it's a portable weather station, but it's specific to the Aloha program, you know, EPA's Aloha program. So what this is it's the same.
Yeah.
So basically, you go, you set up a case, you go turn it on, and then you go to the Mohawk and say, okay, here it is, and then you can.
Yeah, you get some dispersion.
Right,
Yeah.
I'm doing that talk later for them.
That's what we're trying to figure out. It's like,
I'm just trying not to.
when and where is that shot?
It's in the play, I think it's like 1:30 or 2:30 or something. It's called Cabinets.
Okay.
Here, I'll take your,
Yeah, great.
It's so hard to figure out what's where.
It's just, yeah,
Where it gives the time specifically from now, and
yeah,
I've been just like trying to find out where all the stuff is isolated, where they are. It's like next to impossible.
I know, yeah, I was gonna go ask if they had another printed out. updated.
Did you get that here?
No, yeah, there should be. Yeah,
Is that actually updated or?
I think it's updated, got it out. Right.
Yeah.
well, I don't know, it opens up this thing here.
I have one.
Oh, it just literally pulls up our website.
Which one?
Sure, that's, yeah. Yeah. I don't know if that actually has my content information.
Yeah.
Yeah.
I don't have a card. No, they.
Yeah, I mean, the app doesn't show like.
Oh, actually, I didn't.
With
that,
That's something.
It looks like on the app that there's.
Just like
That's expired.
Oh, yeah. I usually have cards. I've been taking care of my dad.
Oh, yeah. Well, and
I wasn't,
Yeah, okay.
I've got this.
Really, by the way.
what's the next?
I'm in the rally.
So we do, the hazmat we built for the military, but it's really specific. But I can also create another program that's gonna go, I mean, you kind of got stuff that you want to do. Yeah, I'm more like, here's the, like, hey, here's a web page, and we'll just send you the data.
Yeah, sure, of course. So we, I guess we're looking at how.
Yeah, and they,
You know, at this point, you just can't. It is. So it's likely.
Well, I want that to be further away, you know, like the,
Point of measurement. Here.
Are they?
I think that combination of both by themselves have limitations, right? So if you're at point source with point measurements, you know, you don't necessarily just the average.
Oh, yeah.
Right.
But how do you combine point measurements and path measurements to have the complete picture you want for the dispersion, especially for you understanding based on more limited measurements of linear point source responses. That's the kind of stuff.
I can get you in my thingy and, some, and we can talk about it, and then if you sound recording.
Oh, sure.
The last one,
We're getting ready.
this is the second.
Yeah, I was just getting it from my.
Yep, let me get rid of the recording for you so we can start a new session.
Okay, so you want us to sit here because.
No, I mean, it'll pick up. You can stand up.
Right.
Yeah, I mean, you know.
Got it.
Recording.